Thank you. Good morning. It's great to follow a great presentation on Mars and what we're looking for at Mars. My career has really been as an engineer. So although I did want to be an astronaut when I was young, a lot of it has to do with I wanted to build the stuff that got us there. So I did have the honor to be part of Space Station for 11 years and manage things like the assembly sequence of Space Station, which was a lot of fun. And then since then I've been working on the Orion program. So what I wanted to do today is really walk through the architecture we're talking about today, Orion and SLS, show you a little bit about where we've been, and what that says about, I think, Orion's capabilities, and then talk a little bit about the future. So I've got a video here to begin with, and then we'll walk through it, and then I hope we'll have a good chance to have some questions so we can dialogue a little bit about where we are. So let's see. We'll go ahead. This first video kind of gives you a background, gives you a sense for the progress of the three big pieces of the exploration system. There's Orion, there's SLS, which is the rocket, and of course, obviously, you got to launch from somewhere, so it's the guys at Kennedy and what they're doing at the Cape. So we'll see a little bit of that. And we put it to music. Everything to music always sounds better, so you'll see. It's a nice video. Now the audio's not working, but I'll describe it. You can imagine there's music in the background. So there's a lot going on at the Cape. This is the ground systems guys. Obviously, the SLS is a very large rocket. We'll talk about that a little bit, but we're basing things off of the same pads that we use shuttle for and also for Saturn V to try to minimize cost. The mobile launch platform is actually constructed. It's not yet outfitted, but then, of course, in the VAB, we've got this building. So we're going to use it. We're modifying it so we can stack SLS and Orion in the same building and not create a new building to make that happen. The ground systems, though, are state-of-the-art. The launch control systems, very flexible. We're using the state-of-the-art for computers to do that, right? Here's the SLS, 5-segment booster. There we go. Remember, shuttle had 4 segments. Now we've made those solid rocket boosters a bit bigger. Engine testing. We're actually going to use the SSMEs from the shuttle on this core stage. I'll talk about that a little bit, but we're doing testing. We're actually building some of the structure. This piece right here is actually an adapter we're going to fly on our flight test in 13 months, but it'll be the same adapter we'll use on the human flights in the future. This is Orion, and you'll see more pictures of this coming up, but there's our pressure vessel for the flight we have in 13 months. Back shells, a lot of harnesses, a lot of tubes to make a system like this work. I'll give you more on that. A lot of thermal control. There's the heat shield. It's a composite skin made right here in Denver, and then the titanium stringers, which give us the strength. They're bonded together, and then we put Avcoat on the back, and I'll talk about that. Talk a little bit about the Asteroid mission too, so and then we get the crew safely back to Earth, which is no small task. Let's see. Okay, so that's so I'm Mark Geyer, and I have an honor to be the program manager, and it's a challenging job but a lot of fun. So this is the context of which Orion and SLS fit in NASA's plan. There's obviously the space station, again, which is flying today, now fully complete, that we're doing utilization on now. It's flying through 2020. A lot of discussion about whether they'll extend that to 2023, 2028, which I think, and personally, I think is a good idea. Since we've invested in it, we should use it. A lot of things we can do as far as learning how to live in space that space station can give us. But you've got to supply it. It's actually, right now, we've got 6 people on board. We've got to give them supplies, you got to get your experiments up, and you got to get the people up and down. Right now we're using both the Russians, Progress and Soyuz, as well as Japanese and Europeans who have cargo vehicles that can take supplies. So we're working with these different ways of procuring systems, commercial cargo, which we've seen SpaceX dock with Station. Orbital is launching their version later this year. Hopefully get the cost down of providing ham sandwiches and experiments to space station. That's a real big deal. We can reduce those costs. We can spend more money then on exploration. That's important for us. People also is another thing we're looking at to try to reduce the cost of buying Soyuzes. So SpaceX Boeing as well as Sierra Nevada are working on ways of getting people to space. And so it's very important for them to succeed to reduce the overall cost that NASA's spending so we can spend that money on exploration. Very exciting stuff going on there. Then, of course, Orion and SLS are what we need to go beyond low Earth orbit. Our requirements are a lot different than a LEO spacecraft. For example, our entry velocities for the heat shield are a lot different, a lot higher. I think they're around 7.9 kilometers per second. We're at 11. That's an example. We need more volume because we're out in space longer. We have you have to be a lot more highly reliable vehicle because you can't have accidents in deep space. You need to minimize those. When you're in low Earth orbit, you can get to the ground pretty quick. When you're at the moon, you've got days to get home, and so that drives our reliability and some of our contingency systems. So I'll talk about the missions that we're working at today. So that's the difference. That's how we fit. We're all part of that same program. SLS and Orion, and the SLS is needed really obviously to give us the delta V, to give us the energy to get to those destinations. So Space Station again is our commercial partner supporting Orion, and SLS can get us to cislunar space. That would include regions around the moon, Lagrangian points, this asteroid that I'll talk about, so kind of stepping stones, and eventually onto Mars. And I know obviously for Orion to be part of a Mars mission, you need a lot more elements, right? Orion is the thing that gets you into space. It allows the crew to enter, but you need a lot of other elements to get to Mars, as you well know. But we're part of that kind of a stepping stone and adding more and more capability as we go forward. SLS capability, it's a large rocket. The beauty of a large rocket, you can do things with fewer launches, which is really important. We see with Space Station that we absolutely can do assembly in space. It can be done. We learned a lot about how to do that, including with partners who have different techniques. But it does take time. It does add risk. So having a large rocket that can reduce those assembly flights is a big deal, and also can give us the energy to get to these different destinations. This is the early version. This will be we call the 70 metric ton of the Space Launch System. This is the one that Orion will use to do the first missions that we can do this Asteroid redirect mission that I'll talk about in a minute on this vehicle. And this will be the first human launch will be on this vehicle. It's a 5-segment solid rocket boosters, 2 of them. It's a new core. That's the new part is the middle. You say core stage in avionics. That's the one new segment. We'll use SSMEs that the shuttle did not use. The upper stage is actually a Delta IV upper stage with stretched tanks. So again, we're trying to use the systems that we have today to keep the cost down, and then Orion is on the top, or the pointy end. These are the different rockets that have existed in the past. You can see the Delta IV Heavy there, third from the left. The Space Shuttle, then of course Apollo, Saturn V, and then the 70 metric ton. The SLS has the capacity then, and is being designed from the beginning to be evolutionary, to evolve into larger capability. You can have different boosters on the side, which could be liquid, give you more capability. Then at bigger upper stages, you can grow to the 105 and 130 metric ton. So the beauty of this, I think we need to remember, we need to minimize starting over again every time and actually evolve the systems that we have. And the beauty about this SLS system is we can do that, and that reduces your cost as you move forward. So the Orion is on the top. This is the part I get to work every day. What you see, I'll start from the upper left. One of the most dangerous parts of any mission, whether you're going to the moon or all the way to Mars, is getting the people out of the gravity well, the Earth gravity well, right? It's a lot of energy to get them into space. So it's also obviously very important that the crew, we don't lose the crew. One, because they're friends of ours, right? We work with them every day. It's tragedy, but also it can have a big impact on the success of your mission, right? If you have a lot of assembled things ready to go to Mars and you lose the crew on the launch, right? It's a big deal. You're going to be shut down for years. So the launch abort system is part of what is different in Orion than shuttle. We can get the crew off in any phase of flight. At the very beginning off the pad, if we have an issue at the pad, all the way through orbit. So the launch abort system actually gets us through the most energetic part of that, where we have a lot of high max Q, transonic flight. It's a 500,000-pound solid rocket motor. It's going to pull the crew off the rocket at about 12.5 Gs. It's not a fun ride, but you're you're alive and you're safe, and so it's a big part of this system. And I'll show you a video of a test that we've already actually done with this system. Underneath that is the crew module. You can see it there in the middle. That's obviously where the crew lives. That's where they live and work. That's where they interact with the spacecraft. We have displays, controls. That's where their suits would be. That's where all their food's going to be, and all the life support systems that keep them alive are in there. Then behind that is what we call the service module. And in the service module, there's obviously the solar arrays, so we generate power. It's also where the main engine is, so where we get our Delta V, the prop tanks, so forth. We also have a set of auxiliary thrusters for reliability. It's also where the big tanks are for air, water, those kind of things are back in the back. Then below that is the upper stage, which pushes us to our destination, whether it's the moon or to this asteroid. And then below that is SLS. So it gives you a sense for all the different pieces. I think everybody thinks that as we go into exploration, we're going to go not just as the United States, but with other partners. Certainly we did it on Space Station, and we learned a bunch about how to work with them, both at the political level, down to the engineering level, right down to the nuts and bolts of how to do that. So we've made an arrangement with ESA, the European Space Agency. They're actually providing that white part there in the back, most of the service module for EM-1, or for our first flight. That's coming up in 2017. So this is the beginning of international cooperation for exploration. ESA will be providing that section, which has the radiators, the solar arrays, the propellant system, and so forth. They get to use experience that they did in building the autonomous transfer vehicle, which is one of the ways Space Station gets cargo to space, is Europe provides that for them. So they're bringing their expertise in that. This is actually a very highly integrated system, though. The service module, the white part and the gray parts never fly by themselves. They're all highly integrated in avionics, control, obviously reliability, everything else. So it's a lot of work for us to integrate this piece and do it well. But to me, it's the beginning of going into space and doing exploration with other partners. So this is our magical mystery tour of Orion. I call it. It's a long history of what we've gone through. But a lot of testing, a lot of choices about land versus water landing, a lot of discussions about avionics, you know, what power with 28 volt, 120 volt, all the kind of things that engineers do to make systems work. A lot of trades early. But going forward, you see there in the middle is Exploration Flight Test 1. You see the Delta IV Heavy. We have a flight now in 13 months. In 13 months, we'll be launching out of the Cape. We'll be flying an Orion system, testing the key 10 of the top 16 wrist drivers, and going 3,000 miles into space. So that's the first test we have coming up. Then in 2017 is our first flight on SLS. It'll be unmanned, obviously, as we test all the systems of SLS and Orion, and we will be looping around high lunar orbits and testing that system. We have another abort test where we test that launch abort system, and we'll fly it at max dynamic pressure and transonic speeds, because that's the most difficult region to control the abort, and if you tumble in that region, your spacecraft will break up. So it's a very dynamic phase that we're going to test our abort system in. And then 2021 is the first human launch. This phasing is obviously budget driven, and maybe we can talk about that later. We could fly these earlier, right, if the budget existed. We recognize where the budget is, right, where the country is making things work for the money they have, and we've redesigned and rephased this work so we can get it done with the budget we've been given. So this is
3, 2, 1, launch.
So this was a test we did to test the launch abort system. This would have been a test off if you were on the pad and you had to get the crew off because there was something wrong with the rocket. This particular test accelerated at 15 Gs. There's 3 solid rocket motors. The first one gets you away. You'll see those at the very top. There's actually attitude control motors. It's actually a solid rocket motor that's using carbon-carbon silicon valves to control the direction of the spacecraft. Then we test all the parachutes, the drogues, the pilots, the mains. It wasn't as close as it looked there. It does give you a sense that we actually reef the chutes. They start with a small opening and then they get bigger. This helps us use the same chute but actually get a very nice gradual load for the crew. Anyway, it worked great. It's a very difficult system. You can imagine the loads are very high as an engineer, so this particular test, all the avionics experienced 15 Gs. At the edge of the spacecraft, it was 180 decibels. because the acoustics of a solid rocket motor like that are pretty high. So all the systems you're putting into this spacecraft to allow the crew to survive in that dynamic have to survive those kind of environments. And so the team did a great job. Our system's designed for this, and that test went great. So that was the beginning. Our next big test, like I said, is Exploration Flight Test 1, which will be in 13 months from today. We bought a Delta IV Heavy to do that. The reason we did that, SLS is still in development. They're not ready till 2017, but we can use a Delta IV Heavy, and it'll get us 3,000 miles into space. 3,000 miles, think about space stations at 200 miles. So obviously we're a lot higher. The reason we're going 3,000 miles is it gets at about 84% of a lunar entry velocity. So we maxed out this system to push the heat shield as close to lunar entry velocity as we could get with an existing rocket. So it allows us to test the heat shield. We'll test entry, navigation, and guidance, which is no small thing. All the parachute systems will be tested. We'll also test some key separation events like jettisoning the LAS. We have some service module fairings that help us actually reduce service module mass, but we have to get the fairings off as we go into space. So a lot of key systems will be tested. Again, we'll do that in 13 months. So the pictures I show you of the flight elements are for this test. Okay, so you might have heard of the Asteroid redirect mission. And they call it redirect because you're not going to capture something and have enough delta V to capture it and bring it back. So we're going to kind of nudge it. This mission, it is currently being assessed, I would say. And the main idea of this mission is what can we do to bring together elements that we already have in our portfolio to do an exploration mission, to really, and then push on all those systems, right, and give us something to focus on. So obviously we're already identifying asteroids. We already have, obviously, robotic spacecraft that can go to asteroids. We have the Orion and SLS systems. So the idea of this then was to combine those and do an exploration mission in the near term. Obviously, the robotic mission would be unmanned. They would go out after a particular asteroid was identified that fit the particular parameters. It would do a capture and then bring it into a high lunar orbit that then the Orion on top of SLS would go to, and we do some EVAs for that asteroid, at the asteroid. Orion and SLS obviously have the capacity to do this. We have all the rendezvous and docking capability. We're made, built, enabled to do EVAs out of Orion. There are a couple of tweaks that you need to do, but basically our system can perform this. I think the harder part is getting the asteroid in this region, and that's part of what NASA's looking at. So again, the beauty of this one is it's the first time that the president has actually, I'd say, blessed or asked for a particular exploration mission that happens in the near term. This is the first one. And so we're working with our boss, Bill Gerstenmaier in Washington, and with the Science Mission Directorate to flesh out what it takes to do this mission. There are a lot of, I know a lot of you that have a lot of ideas of how to get to Mars. There are a lot of different concepts. There's one particular one that you might remember, Doug Cook, done a lot of assessments on how to get to Mars. His team had an assessment of one particular one. A lot of the studies they've done had a 6-person crew. When you actually get to the ground, Orion can handle 6 people. It's actually its base diameter was set based on being able to hold 6 people. So it can participate and would participate in a Mars mission, assuming obviously that there were other elements like the propulsion and hab modules. You obviously can't sit in Orion all the way to Mars; it's too small. So we envision Orion as being part of that. And again, I think it's important. While you might be able to optimize a different capsule system for a particular Mars architecture, I think it's important that we take what we have and evolve it to these different missions. And I think it's much more sustainable architecture to do that. So Orion can do these early missions like we talked about, potentially this asteroid. We can go to the moon. We were built from that from the beginning. We can do these Lagrange points, and it can fit into one of these architectures. So I think that's my opinion. This is the program history. This is not so since we started what was originally called CEV, Crew Exploration Vehicle, we've had 2 presidents, 3 administrators. I think there have been 6 AAs, associate administrators, 3 program managers. The other thing, if you look in the green line, under that, there's been a lot of changes for CEV, Orion, and PCV. At the beginning, under Admiral Steidl, the original concept off. We would have we pick two contractors, they'd fly it off, kind of like the Army and the Navy, or excuse me, Air Force and Navy do fighter jets. Then we changed administrators, and Mike Griffin said he didn't think we needed to do that, and our focus then was to fly as fast as we could to space station. So we began, and actually in the contract that was awarded, it was very much focused on flying early. When the money was not there to fly early, then we changed, Mike changed our focus really to what I call a legacy vehicle, which was to have, I would say, more elegant design. We switched to 120 volt. We added a phased array comm system. We investigated things like composite crew module. We changed our avionics system. So to me, it's more of a long-term design in a sense, if you think about it. Then we were under Constellation at the time to do that. Then, if you remember, in 2010, it was proposed that we be canceled. Then we survived that by showing again that Orion meets the requirements for exploration vehicles. And they changed our name though. We were MPCV for a while. We have a new rocket, which is SLS, which I think is a better actually rocket for exploration. So that part is good. So this is not to whine or to say it's hard being a program manager, but to say this is the reality of, I think, the political landscape. And you could pick any one of those and say, geez, I wish they hadn't done that, but I think this is what happens when NASA, human spaceflight things are very visible. The budget is very tight. Everybody wants to put their mark on human spaceflight. So this is the way it goes. So I think the key, what I got out of this is that Orion has survived these, what I would say, changes, machinations. We have a capsule that can do the destinations. We're on our 4th destination, and we can do that destination as well. And so physics still wins, but politics is still is probably a close second as far as driving what happens to us day to day. So I think this is the environment we live in. Certainly, space stations saw the very same kind of thing. So let's talk a little bit about now the fun stuff about the hardware. So we're going to fly in 13 months. This was actually an acoustics test that was done here in Denver. Remember, I said that when the solid rocket motors fire on abort test, you're seeing about 180 decibels at the ring. So acoustics is a big driver for the structural design and for the components. So we built a ground test article and tested an acoustic chamber right here in Denver to validate our models. We do a lot of wind tunnel testing. This was a particular test for the drogues. I think this was at Ames. The parachute system is an interesting system, and then it actually assembles itself as it's falling. If you think about it, the parachutes come out and they have to unfurl and they can't run into each other, and there's a lot of interactions between the parachutes, and we reef them. We change the hole size with a pyrotechnic device, right? So it's very dynamic. So we do a lot of drop tests where we fail a chute, where we don't open one of the chutes correctly, where we change our descent rate, those kind of things. So we do a lot of parachute tests to make sure it works. Mass is a big deal when you're flying beyond low Earth orbit, because every pound that is in your spacecraft, you have to accelerate it to wherever you're going. You have to decelerate to come home, so it's a big deal. So we did these drop tests to make sure we understood the landing loads on the primary structure. Primary structure is your heaviest part of the vehicle. By doing these tests, we were able to skinny out the structure to get it as thin as possible. A lot of tests using facilities that exist. This is the NBL in Houston, where we do it. They do a lot of underwater EVA work. We also took our mock-up in there and did a very cheap test on these uprighting bags for Orion. These are the search and rescue guys testing out the Orion. We won't actually pull the crew out in the water. We're working with a ship that's actually a well-decked ship that they flood the deck, and we put the capsule in and unflood it so the crew can just get out. But in an emergency, you need to know how you might get them out, so we have search and rescue guys looked at the capsule so we could make changes to the outside before we started doing the design. This is the pressure vessel of the system that'll fly in 2013. These are back shell templates where we drilled holes, but it gives you a sense for what the back shell looks like. These back shells will be covered with tiles, much like the shuttle. The heat shield on the bottom, obviously, at the speeds we're gonna see are actually much higher than shuttle. It's much closer to Apollo, so we use an ablative material called Avcoat, and there's a honeycomb structure here that's filled in with this Avcoat material. So we're actually within 2 weeks of being totally done with his heat shield, and then we'll be shipping it down to the Cape. Underneath that heat shield was a composite laminate. This is only exciting if you're an avionics guy, but this is where all the computers are being tested in Denver, right here. In the middle of that is the actual engineering development units of all the computers and the power distribution units and simulators of the end effectors. And the back is a copper looking building, which is where we actually put the common track system. So this is where we test all the avionics and run all the software before we put it on the vehicle itself. And this is fully operational. These are main structures. The top, it looks a lot like the launch abort system because it is. That's the flight structure on the right that we're testing it in the structural test facility in Sunnyvale. And on the bottom are these service module fairings. Again, mass is so important that the service module itself, we actually put fairings around it, and those fairings help take some of the load during launch, and then we get rid of them. So the actual service module that flies to the moon or beyond doesn't have to be as strong as it would have to be in an ascent. So it's a great idea, but these are the first time that fairings will be jettisoned under load, so it's a new concept, again, to reduce mass. So we do a nice fairing jettison test in Sunnyvale. It was cool. 2 of the 3 worked. One of them didn't. We actually had an interference with one of the pyro devices, which we fixed. But we do a lot of testing to make sure that the system's going to work. And we'll actually fly these fairings and jettison them again on EFT-1. So I think that's the main. That's the end of the main pitch. There's another video here which talks a little bit about what it's going to be like to launch people, and then we'll be open for questions. So maybe the audio will work here.
From the Kennedy Space Center in Florida at T-minus 3 hours and holding. And we're now in the final 5 hours of the countdown. Crew going down the elevator has been used by the astronauts ever since Apollo.
It is great to be in Florida today. The rocket is ready to go fly. The team is ready to go fly.
The new mission is quite a bit different than the shuttle mission. The next mission is to go beyond low Earth orbit.
We're at T-minus 2 hours, 38 minutes, 6 seconds and counting as the crew approaches the launch pad.
Not only for our expanded knowledge of the universe, but for the improvements you have contributed to on Earth. Have an excellent mission and Godspeed.
Crew ingress and work at this time.
Connect. Flight crew OTC, close and lock your visors and initiate OT flow.
T-minus 10, 9, 8, 7, 6. All engines up and burning. 1, 0, and lift off.
So our job is to make sure it's not just a movie, right? That it actually happens, and so that's what we try to do every day. Yeah. How do you guys?
So as we take questions, if I could just ask if Dr. James Ray is in the room, if you could come join me up front, and we'll have our folks walking around with the mics. So first question here.
Hi, Mark. What about the SSMEs? Are you funded for follow-ons to keep the supply open for future SSMEs?
Yeah, so that's great question. So we're going to reuse the ones that shuttle ended up or when they were done, we had extras, so we can fly several flights. So Todd May, who's the program manager for SLS, in his budget, he has the development line to update those and start making production of new units. So they're in his budget plan. But at the beginning, we can use the ones we already got, which helps us in the early phasing. How do you want to pick the question? Do you guys want to do it? Okay, thanks. I'll repeat your question.
You said that the escape system, this would be the first time, ever, could save the crew through all of the launch phase. Up to which date would that be possible? Up to which phase of the mission would that be possible?
So basically what I was speaking to was ascent. Now, Apollo had the system too. We think there were probably some black zones in the Apollo ones that may not have worked, but so that the intent is through ascent. So we can abort early. We use the launch abort system in that very dynamic phase. Later on, we can use the service module to get the crew down and close to continents. Right, we don't want them in the middle of the Atlantic. And eventually, you can abort to orbit and get him up there, and then you get more time to decide what to do. We also have a contingency case where Orion is built to handle a depress. So if you're around the moon and you get a depress, we can handle a depress for 170 hours where the crew is in a suit. And they're being fed oxygen and CO2 removal through the ECLS system. So that's one of the contingency cases we can.
Who makes the parachutes, the main parachutes, and also are the boosters going to be recovered, the solid rocket boosters?
So Airborne makes the parachutes. It's actually managed by Johnson Space Center, NASA folks who are the experts on the chutes, but Airborne actually does the manufacturing and packing. The Space Launch System guys did a trade on recovery, and they actually found it was cheaper to dump the boosters. This is one of those challenges that when you've recovered them forever, and when you can recover them, you can expect the heck out of them. People are struggling with that a little bit, but I think it's one of those things we need to move on. We have a lot of experience, so they will not be recovered.
First, with all the political changes, how's your blood pressure? But the other thing is, how many units, how many crew modules are you funded for at this point?
So through that sequence there, we have EFT-1, then we have EM-1 and EM-2, and I have a structural test article, so there's 4 in that. We'll reuse the EFT-1 article. We'll actually reuse for that AA-2 test, so we try to reuse as much as possible. So basically 4. That is a challenge, as you can imagine, ramping teams off and ramping them up when you're spread out that much, and it does make it inefficient cost-wise, but that's the plan we have to fit.
Is the video available on YouTube?
Yes.
Great. It's really beautiful. It ought to be shared with as many Americans as possible to up the NASA space budget. Thank you.
Great. Thank you. Yeah, I'll let the team know. This gentleman. If you say it, I'll repeat your question. Sorry, now there's a mic. Yeah.
You didn't show the Falcon Heavy or the Dragon Rider that should be available like next year, but you showed other stuff that'll be ready in about 5 or 6 years.
I showed the rockets first that were in the past and that were capable of doing our exploration missions, right? So that's what I showed. Not all of the rockets that exist or might exist.
What's the biggest challenge that you face from not having one specific destination in mind?
Some of it, I would say, is actually morale. You know, engineers like certainty. And we all look back in Apollo and say it was so clear back then. But reality is, and I talk to my team, I say, in the next few years, Orion, the capability to go into cislunar space, whether I was going to with a lander to the moon, or whether I was going to Lagrange point, or whether to this asteroid, or eventually fitting part of something else, the majority of our work is exactly the same. You know, I've got to make safe, reliable systems that can support the kind of stuff people need to do in space. So what I do for that is let's keep the team focused on near-term things like this test we've got in 13 months, right? It drives a sense of urgency, keeps the team making decisions, allows us to advance the state-of-the-art in engineering, and we kind of let them do their thing up there in supporting that. But again, because we can do so many missions, I think that gives us hope. We're going to have good missions to do. It's just a matter of which ones they'll settle on. Sure. Yes. So in 13 months, we'll launch on a Delta IV Heavy, and we'll go to 3,000 miles. So it's basically to push on the heat shield, but we'll do all the entry, navigation, and guidance, parachutes, and those keep separation events that we talked about. So while SLS is in development, we can wring out all those systems, and if we find issues with them, we can fix them before it gets real expensive later on, where everybody else is waiting. So I can get into low Earth orbit with a Delta IV Heavy. Yeah. They just can't get me to the moon and other places.
Are you still designing the capsule for reusability, and as a practical matter, do you actually plan to reuse them?
Yeah, so it's funny thing, the expensive stuff is all the guts inside. If you've done one of these, all the avionics, the pumps, the fans, the other things that are high reliability, high radiation strength parts, that's where the expensive, all that stuff we're going to reuse. I mentioned that the EFT-1 flight article we're actually going to reuse again on AA2, so we try to reuse that whole test article for the next one so we don't have to build one. The structure itself, when you go from EM1 to EM2 to EM3, in my budget, I don't assume I'm reusing it because I haven't flown one yet, and I need to see what the loads look like, and actually after we recover it, you know, in the water and those kind of things. But we'll inspect the first few, and if we're finding that the loads are within family, we're not seeing strange things, and we're not seeing corrosion, then absolutely we'll reuse them. There's some things like the tiles we'll have to take off and replace. The heat shield obviously gets ablated, but a lot of the rest, the pressure vessel and those kind of things, we want to reuse as much as we can.
So are we still into water landing return because it's the best, or because that's what we tried so many times and it seems to work? Was real consideration given to landings?
Yeah, great question. So there are a lot of pieces to that. One of it, if you think about land landing, we did a lot of testing up front, and these airbag technology is much better than it was before, and you can actually do a pretty good job of landing on airbags. There's a couple things. It's heavy, right? So it was a couple thousand pounds heavier, and when you're pushing all this stuff to the moon, it's a big multiplier for us. The mass is a big deal. So it was heavier. It's more complicated. I have to jettison the heat shield before I deploy these airbags. So it adds complication, it adds risk. So we find actually getting the crew to the surface, it's safer and easier to land in water. Another thing is downmoding. If you're a G&C guy, you know, as you're coming in and you've got problems with your trajectories, you can do a ballistic trajectory and come down fast. If you're going to land on land, you got to be careful when you do that, because you're going to land, you can't land in Los Angeles, right? Most of these spaces would be in the desert. So you're down mode, you have a lot more opportunities in water. So we found that landing in water was safer to get the people to the surface. The issue with water is getting them out of the capsule while they're in the water, right? So now we've got this idea with this well-deck ship where we're actually going to pull them into that, and then we actually unflood the deck, and so the crew actually gets out on the deck and they don't have to get out in the water. So we think we've got the best of both worlds, but it's really a lot of work, a lot of design trades to find the best answer. And also our G&C is so much better now. We don't need the whole Navy with a bunch of helicopters, right? It's one ship. It's one ship, so. Yes, sir.
Excuse me. I know the Dragon is being built to go to service the space station, but Elon Musk is always looking ahead, and he really intends this to have capability for deeper space as well. Can you contrast, do you know enough about the Dragon to contrast the capabilities between it and Orion?
So let me say, first of all, that they're doing a fantastic job, and it's really important that we succeed on getting people and cargo to space station cheaply, so we have the money to do exploration. Our requirements are a lot different. Even though we might look, they're painted white and they're kind of pointy, they're a lot different. Except I mentioned the entry velocity is quite a bit different, right? 8 compared to 11.5 for us. So that changes certainly the thickness of the TPS. It may even change the kind of ablator that you're using. Ours was judged by the TPS experts at NASA to be the best for the missions we had deep space. You need more volume when you're out there longer, right? We have a bigger spacecraft because the crew, you got to stow a lot of stuff, and the long duration you have to do exercise and other things, and you got to have these EVA suits. So the volume's important. So our volume is bigger, and we're driven a lot more by reliability because you're a long way from low Earth orbit. So you know, he's doing a fantastic job. He's got a lot of good ideas, but the capsules today are fundamentally different as far as the requirements they're meeting. Now, I think there's a lot of things we can learn, Lockheed, Boeing, others, on the way he's saving money. And so we're looking hard at figuring out how he's bringing his costs down on some of the components that he's building.
What percentage does the core stage make it into orbit, and how much additional emergency fuel do they have?
I couldn't give you the breakdown of if you didn't have the solid rocket boosters, how much could the core do? Is that what you're asking me?
No, I'm asking how far it makes it into orbit, just the core stage when it's jettisoned, and how much emergency fuel does it have aboard it?
So it can get the upper stage and Orion all the way to low Earth orbit, which is a bit higher than space station orbit, and that's where we check the systems out before the upper stage pushes us. So it can get all that capability up. I don't remember the mass of the upper stage. I can probably get that for you. But it's made to use all the engines. Now we are talking about an engine out capability in case they lose one that we don't automatically have to do an abort. We might be able to abort to orbit. In that case, it depends on when they lose that engine.
I assume that you haven't looked at all at using Orion to land payloads on Mars or anything like that. You're probably not even allowed to, considering it's not in your requirements. But has anyone looked at that at all? Would it be capable of doing something like that? What would you have to change about it to be able to do that?
Yeah, as far as being the cabin where the crew sits while they would land on Mars, I guess is what you're saying. Certainly, it has the volume. It has the ECLS system to do that. You would have to look hard at your durations, right? How much your life support system durations are. I think you'd want to trade whether that was the best use of your return capsule, because it's the only thing that gets you back to the surface of Earth. And maybe you could do one, maybe a lander that might be smaller for the duration. Yeah, the service module itself is not built to do landings, so it would have to be modified to do that. Yeah. To get the thrust levels you need to do a soft landing, that kind of thing would be different. Yeah.
It seems that you would be able to reach the space station before the SLS is available. Are there plans to use Orion to fly American astronauts up and down from the space station as soon as the capsule is ready?
So no. Orion can get to low Earth orbit. Our mission today is not to support space station, although the appropriation law, Congress said they want us to be a backup. So in theory, Orion has all the capabilities. It can dock. It can loiter for a long period of time. It can sit in a quiescent mode for a very long period of time. So and our shields, our back shell, is protected against MMOD. We meet the requirements for MMOD at space station, which is actually a pretty big driver. So it can do the mission, but again, we're part of the strategy where we're trying to get cheaper delivery of crew to space station, and Orion's built for exploration, so it's bigger. It has higher reliable systems. The heat shield is bigger than it needs to be for LEO, and so it's not going to be cost effective to do that. So the plan is today, no. Yeah. So we really need those commercial guys to come through with cheaper than Soyuz costs to get the cost down, and their requirements are simpler enough that really helps them and enables them to do that.
Sir, could you please elaborate more on the EVA capabilities of the capsule? I think I heard you say something about adapter was needed.
There's no So for an EVA, there's no adapter needed for the EVA. Orion was built from the beginning to have a contingency EVA capability. If you remember, when we started out, we had a lander. You might remember lander under Constellation. So there's a contingency EVA where the crew is in the lander and you can't get the hatch open. So you go outside to come back into Orion. So we had to be able to depress the cabin, open the hatch, and then for the crew to get in and then switch over to Orion Eclipse. So all that is in the design. So when we did this asteroid mission, we said, okay, well, we can use the cabin as an airlock in a sense. It's not an extremely efficient airlock, but it's better than bringing the mass of an airlock, right? We can do it now. So the system's designed, they'll be tested to be under depress and operate, all those kind of things. It will work. It'll have to because we had the previous requirement. What we'll probably need to do, though, it's a bigger volume than you would normally like for an airlock, and you're going to lose that air. We don't have a pump to save the air. So we'll have to bring another tank, probably, and we've done an assessment. It could be an internal tank where we can then repress. So right now we can handle 2 contingency represses. Now we're bringing the tank. We can actually do the EVA. So that's really the only change we need to do to make this work. So that, to me, it's, again, an example of using what you've got and tweaking it to add new missions. Yes, sir.
What kind of fitness regimen and equipment are you going to bring up?
So it depends on the duration. Right now, we won't have the volume to do the kind of things like a treadmill and the iRid that they have on space station. So a lot of this probably, and I'm not the expert on this, but a lot of this would be the kind of stuff the crew can do with themselves. You know, as far as what do you say, resistance. The longest duration we're looking for with a crew is absolutely inside is 21 days. So in that time period, you don't need to do a lot. Again, for the longer durations like Mars and so forth, you're going to need a HAB, which is going to have exercise equipment in it. Great. So we may have more capability than we thought we did. Good, yeah, great.
How many people do you have working on the program, and what is your total cost to date?
Could you say it again?
How many people do you have working on the program, and what is your total cost to date?
Yeah, so let's see, on the Lockheed side, gosh, I think Lockheed has 500 to 600 people. On the NASA side, we have 400 people, I think, something like that. So it's in that range, 1,000, maybe 1,300 a year, in that range. Total cost depends on where you start. You know, right now my budget per year is around $900 million. Yeah. And we're working hard. We deleted, we deleted and risk mitigation fixed about $1.7 billion of stuff to get under this plan here today. We reduced our staff by 35%. We took more of the NASA guys who were doing oversight and turned that work into inline work, in other words, doing products that Lockheed now did not have to do. And yet it still helped us do our oversight job. So we're doing a lot of things to make this as affordable as we can. Yeah. Yes?
What's the design cabin atmosphere, and what are the tolerances? How could you deviate from that? In other words, if you're currently designed for 10 psi, could you go to a 5 psi Skylab type atmosphere if you wanted to and allow more EVAs? What is your brackets there?
So right now we're at 14.7. Yeah, we're spec'd for 14.7. It's the same as space station. Yeah, that's true. So we were to match space station at the time, and so that was our design. For the 21 days, it works. We have looked at 10.2, which would make more capability for EVA, and I think the question there is really a long duration at 10.2. There are some concerns with the, let's see, I would say the space dock guys as far as looking at things it does to the eyes and so forth. I think that's a new thing. So we can do it. Well, we'd have to go back and look at certifying the equipment inside for the 10.2, but I don't think that's a big deal. But right now we're spec'd at the space station atmosphere.
In the design, was there anything that the budget that you really wanted to do, but the budget just wasn't there, and you had to say, sorry, boys and girls, we can't do it for this one, but you really, really yearn to do it?
I would say that there's no technical thing that we've deleted that we thought was stupid. I can tell you we argued about a lot of things, about what was absolutely required. If I had the money, I would go faster. There's nothing that drives the team better and gets us doing things than going faster. I would just go faster. I wouldn't add content. That's what I would do.
As a manager, how do you balance your ability to improvise and cut costs and still deliver with not falling into a self-fulfilling spiral where every time they say, see, we cut the budget and you did this anyway?
Yeah. So when you succeed, do they say, "Well, you were fat before," right? That's part of the discussion that you have to have. I think the big driver you see, even with the significant reductions we did, is that the schedule did move. And when we saw the schedule move significantly, remember we were in 2015 before, now we're in 2021, and a lot of that is because we had to push. Well, all my reserves are at the end. Like, we can talk strategy about how you do that. All my money reserves are at the end. That's part of it. I pushed all my qualification past EM1 because I really want to do that unmanned flight as fast as I can. Those are the choices that we made. We also added this flight test. The flight test didn't exist. EFT-1 did not exist under Constellation, but I was worried that we spread everything so far out, we were going to lose the focus of the team. So we did this unmanned EFT-1 here now within 13 months. It was a big deal. So we try to keep being aggressive, and so we try to pull on those things. Hey, look what we have done with this constraint to keep things moving. So yeah, it can be. You can't win in some ways. If they're against you, they're going to find reasons to be against you, no matter what they do. But another question? Yes, sir.
Have you considered a simple inflatable extension module that could be used to add living space to the Orion?
Yeah, great question. So there's actually an experiment on space station where they're gonna, I think it's with, now I've forgotten his name. No. No, it's a guy in the desert. Bigelow, say, thank you. I should know that. Anyway, so there's a space station experiment where they're going to actually do an inflatable. They're going to test it on ISS. It's a technology that started with I think it was Transhab at JSC. So if that works, and then they can start, I think, fleshing that out a little bit more about how to add structure, secondary structure, and those kind of things. I think you absolutely could do it and extend your durations. Yeah. For us, the limitation is really, one is habitable volume, right? Then the stowage volume. The thing with an inflatable is you can't stow things in something you're eventually going to inflate. And so as you expend your duration, you've got to have food and water, and that's got to go somewhere at the beginning. Right, to a degree, to a limitation. So it depends on how much you think this inflatable is going to extend your duration. So I think it helps, absolutely.